Hello everyone and welcome back to the channel. In today's video, I will show you how you can train or fine-tune your own large language model to give it the ability to perform reasoning, and that's using the GRPO algorithm for reinforcement learning. And the only requirement is that you need the GPU with at least 7 GB of VRAM, and you can perform the training either locally if you have the GPU, or you can use online free kernels like Kaggle or Colab to follow along. Now, if you're not familiar with the GRPO training technique, don't worry. I will explain it intuitively without going too much into the technical and mathematical details, so you don't have to worry about that. Now, I think that I can safely assume that you've most likely heard about the DeepSeek model, and in fact, the DeepSeek R1 model was trained using this technique to give it the ability to perform reasoning and think before answering. So let's see how the GRPO training algorithm works, and how you can run it on any large language model you want. So the GRPO training technique was introduced about 1 year ago in the paper of the DeepSeek math model, where it was used to train a 7 billion parameter model that rivals the performance of huge models like GPT-4 and Gemini Ultra on mathematical tasks. And earlier this year, it was used to train a general-purpose large language model, the DeepSeek v3, on the task of reasoning. And this new model is called the DeepSeek R10. Now, the most notable achievement is that it was trained without any supervised training. So they took the base language model, the DeepSeek v3, which is not trained on any specific task, and only with the GRPO method, they made it able to reason and provide accurate answers. Now, usually the training pipeline goes first through a supervised training phase. Then we continue the training with the reinforcement learning with human feedback. And in both these stages, there's plenty of work that's required and done by humans. But with the GRPO training technique, we can go directly from a base model to a reasoning model in only one step, and without the requirement of any human intervention or feedback. So how does that actually work? Now, as I said, GRPO is a reinforcement learning algorithm. That means it uses a reward-based approach to train the model. Usually in reinforcement learning with human feedback, the human checks the output of the model and assigns a reward for it. But in this approach, it's actually done automatically using predefined reward functions. Now, as we will see, these reward functions focuses mainly on two aspects of the output, the accuracy and the format. The accuracy rewards checks the correctness of the answer given by the model, and in case of math or code-related questions, that is very simple to check, and that's why it was first introduced for the DeepSeek math model, which is trained for math questions, and the format rewards, where we check whether the model provided the correct format for the output. So it's actually indicated to the model in the prompt or system message that it must provide the reasoning steps between specific tags, and the answer also should be between specific tags, and we will see that later on. So basically, only with this prompt and these kind of reward functions, the model is incentivized to perform reasoning, and it learns to do that and even improve its reasoning autonomously without being told to do so. As you can see here in this part of the paper, where the model realizes that it needs to reevaluate its work and maybe reiterate. Okay, so far so good, but we know that any training algorithm of deep learning models requires some kind of an objective function that we can use to update the weights of the model so that the model trains iteratively. And in the GRPO algorithm, the objective function, or you may call it the loss function, is the following. So here I will give you an intuitive explanation of this expression without discussing the math behind it, so that you have a general idea on what's done here. So first, we can see here that the objective function depends mainly on theta, which are the weights of the model, and our goal would be to maximize the objective function. Next, we have this part of the equation. Here, the E stands for the expected value. You can think of it as some kind of an average that we can calculate based on the data we have. Then in this part, we say we would like to sample a query from the dataset, and then using that query, we sample a certain number of responses using the model from the previous iteration of training. So here the model is noted as P theta old, and that stands for the old policy, and here policy basically means the model. So old refers to the previous iteration of training. And as you can see, using the queue or query, we sample G number of outputs. And based on the policy we have, the query we sampled, and also the outputs we get, we will calculate some sort of unexpected value. And we can see beneath it how it's actually calculated. So let's start with the most important part of this expression, which is this ratio. So here, we actually calculate or express how much the current model is confident in the given output, and then we divide it by how much the old model is confident in the given output. So we're actually kind of comparing the confidence between the previous iteration and the current iteration of the training, and then we scale it up with the advantage, which is denoted here by A. So the advantage is calculated as such. For example, we have a prompt, and here we have the completions that we generated. So we generated a certain number here, for example, 4 completions. And then we get the reward based on the reward functions that we defined. And by normalizing these rewards, we get the advantages. And it actually indicates how well this output is rewarded compared to the average of the output distribution. So basically we said we generated G outputs, and we compare the reward for each one of these outputs with the rest of them, and that's what the advantage entails. So that's the main part of this expression. The next part is actually the same as this one, except that we're performing a clipping operation with 1 minus epsilon and 1 plus epsilon. And that's actually used to prevent the current model from deviating a lot from the previous iteration of training. And then we subtract the KL divergence, which is a term calculated to penalize the strong deviation of the current model from the reference or base model. So in case of the DeepSeek R1, the base model was the DeepSeek V3. And that's it for this expression. It's quite simple to understand. And here we have a simplified representation of how it's calculated. This is an image from a Hugging Face blog that you can find in the description. It's quite informative. And you can see when we have 2 prompts, how we can calculate the objective or the loss. Alright, so enough of that. Now let's move on to the code and see how we can perform GRPO to fine-tune LLMs. So here we have the notebook. It's actually a notebook from Unsloth, which is a Python library that enables fast fine-tuning of LLMs. And here you can find the link of the list of notebooks from Unsloth. As you can see, we have notebooks for Colab or Kaggle, and you can pick either one to follow along, if of course you don't want to set up the environment locally. So the notebook I have here is the one for fine-tuning the Qwen 2.5 model. Now I have made few changes to be able to run it on my machine, but before we start with the notebook, you should know that if you want to run it locally, you need to set up an environment for your own PC configuration based on the version of CUDA you have and the operating system you have, etc. So you need to check the compatibilities between all the libraries you will install. So here I included some instructions on how to do that for Windows users such as myself. And I know that it can be frustrating with all the dependencies compatibility issues. So I included the Conda environment that I used, and you can use it of course if we have the same version of CUDA installed. I'm using the CUDA version 12.4. So if you have that and you're running this notebook on Windows, you can clone the environment and start working right away. But if you don't have that, you need, as I said, to check for the compatible versions for each library. So as you can see here, for example, when you're downloading the Xformers library, you can find here how to install each version for the CUDA version that you have, and for the OS that you have as well. And here also, for example, if you're running this notebook on Windows, you need to download Triton for Windows. And you can find here the version that is compatible with the CUDA you have installed. And I've included also some guiding steps on how to set up your environment. Alright, so now let's move on to the next step. Here we have the preparation of data and model for training. So first of all, I would advise you to set up a weights and biases account so that you can monitor the training process. So here we import the libraries to set up our weights and biases connection. So we import the weights and biases key, and then we perform the login and initiate the project. Then we need to download the base model and set up the LoRa configuration. So here I set this variable to 0 because I've encountered some issues when downloading the model locally. But if you're running this notebook on Colab or Kaggle, you don't need to include this line of code. Then we import the fast language model and fast patch RL from Unsloth, and we patch our computer to enable the fast free fine-tuning. Then we set the max sequence length, which is set here to 512, and you can increase it if you want longer reasoning traces. Next we have the LoRa rank. It's a hyperparameter that you can tune. Choosing small LoRa rank means faster training but lower performance, and choosing higher LoRa ranks means slower training but much better performance. So here it's suggested to choose 8, 16, 32, 64 or 128, and here I chose 64 because when I tried with lower than 64 LoRa ranks, I was not satisfied with the results of the fine-tuning. So next we can download the model. Here we're using fast language model from pre-trained, and we're downloading the Qwen 2.53 billion model, and we simply indicate the max sequence length. We load it in 4-bit, and then we set the fast inference to false. So this is actually the parameter that you would need to set to true if you have VLLM installed. And since I'm using Windows without WSL, I can't download the VLLM library, so here we're setting it to false. Then we set the max LoRa rank and the GPU memory utilization. Next, we set the LoRa configuration. So here we use the getPeft model, and we pass the model that we just downloaded, as well as the LoRa rank and the target modules. So here we're passing all the modules to fine-tune, but if you have an out-of-memory error, you can try removing the QKVO target modules. That would probably solve the out-of-memory error, but of course that would decrease the performance of the model. Then we set the LoRa alpha to the LoRa rank, and we use the Unsloth gradient checkpointing. Then let's move on to the next part where we get the dataset and define the reward functions and the training prompt. We start by setting the system prompt. We say respond in the following format. So we have the reasoning part first between the two reasoning tags, and then we have the tags for the answer. So the model here is asked to perform reasoning and put the different thoughts or chain of thoughts that it produces between the reasoning tags, and then when it arrives to a certain answer, it should put it between the answer tags. So this is the system prompt. Then we have the extract answer function. So this function, we use it to extract actually the answer from the output generated by the model. Next we have the extract hash answer. So this is the dataset we're using for training or fine-tuning, the GSM 8K. So if we look here, we have a question and an answer. And as you can see at the end of the answer here, we have 4 hashtags followed by the answer or the integer answer. And this is the case in all the questions, as you can see here, here and here, etc. So each of these questions have an integer as an answer. So this is the format chosen for this dataset, and we need this function to extract that answer, to compare it, of course, to the answer provided by our model. So then we have the download GSM 8K dataset. So here we're downloading the dataset and we're pre-processing it so that we can pass it to the model. So here we're creating a prompt for each instance in the dataset where we have a system message with our system prompt. And then we have the query or prompt by the user, which is the question from the dataset. And finally, we extract the correct answer from the dataset using our extract hash answer. And that's how we're loading and pre-processing the dataset for this task. Next, we have the reward functions. So the first reward function is a correctness reward function, where we would reward the model if it gets the correct answer. So we would extract the answers from the generated output and from the dataset. As you can see here, if R equal A, where A is the correct answer and R is the extracted response from the output of the model. So this is the correctness reward function. Then we have the integer reward function, where we check if the answer is actually an integer. As we've seen earlier, the dataset contains only integers as answer to each question. So we're creating a reward function for that. Next, we have the strict format reward function, and this function checks whether the LLM generated an output following the structure that we indicated in the system prompt. So it checks whether the output has a chain of thought between the reasoning tags and an answer between the answer tags. Next, we have the soft format reward function. This is the same function as the strict format. The only difference is that here we don't check for the new line character in the pattern, and that's why it's called soft format. Next, we have the count tags function. So here we're counting the number of reasoning and answer tags generated in the output. Next, in the count reward function, we use the count tags function to either reward the model positively or negatively for the number of the generated tags. So we actually want from the model to generate only one reasoning and one answer tags, and that's what's going on here. So these are the reward functions, and using only these functions, we can train the model to perform reasoning. And as you can see here, the only indication that we want the model to reason is that we impose this reasoning tag, and we will see how it will perform after training. So next we move on to the training. So here we set first the GRPO configuration. As I said before, I'm setting the use VLLM to false since I can't use it on this machine. Next, we're setting the learning rate and the optimizer parameters. So we have the Adam beta and weight decay, warm-up ratio. We have a cosine learning rate scheduler, and we're using Adam W 8-bit optimizer. We're setting the logging steps to 1. Next, the most important parameters here that you need to tune for your own usage are the per device training batch size. So for example, if you're running this notebook on Kaggle, you can get 2 free GPUs that you can use, NVIDIA T4 GPUs with 16 gigabytes of RAM each. So you can set, for example, here the per device training batch size to 2. But since here I'm running it only on one GPU with low VRAM, I'm keeping it at 1. Next, we have the gradient accumulation steps. So this parameter would only smooth the training, so the model would not be updated as much, but this would require much higher VRAM. So also this parameter I would keep it at 1. Next, we have the number of generations. So as I explained in the GRPO training algorithm, for each query or each prompt, the model would generate a certain number of examples. So here I'm setting it to 3. With higher number, you would achieve better performance, but that would require a much higher VRAM. So here I've tested it, and for me, the max I can set is 3. Next we have here the max prompt length, and that depends on the dataset you're using. If you have longer queries from other datasets, you need to increase this number. And then we have the max completion length, and this is the maximum length of the output that the model can generate. So here I'm setting it to 400. And then we have the number of training epochs. You can leave it at 1 to perform a full training run over all the dataset. Next we have the max steps. So here the max steps indicates how much steps the model would take to finish an epoch. So here I'm setting it to 350. The model performed much better when I tried steps over 300. Next we have the save steps. So after each 150 steps we save a checkpoint of the LoRa. And then we have the maxograd norm, report to weights and biases, and the output directory where you would like to save the outputs. Next we create our GRPO trainer. So we pass the model, the tokenizer, the reward functions, and the training arguments, as well as the training dataset. And now we're ready to start training. So we execute the trainer.train. And you can monitor the training from here, from the notebook. You have the training loss, reward standard deviation, completion length, and KL divergence. Or you can follow and monitor the training from your weights and biases account. And let me show you how the training went. So here first I have the training with GRPO locally. And then here we have the training with GRPO on Kaggle. So I performed the training both locally and on Kaggle to compare the results. So here first we have the count reward function. You can see an upward or slightly upward trend. And by the way, you can go over here to the parameters and set the smoothing to running average. This way you can easily visualize the trends. Because we set the logging steps to 1, that would induce much fluctuations in the curves. And as you can see here, when we use the moving average, we can clearly see that the upward trend. It's a slight upward trend, but you can see we started around -0.02 and then we reached at the end around 0.1 reward for the count reward function. And we have all the curves for the other rewards. So here we have the int reward function. So you can see that the model learned to answer with only integers, and we have the correctness as well, which is actually the most important reward function. So you can see that the model started giving wrong answers, and then it reached the point where it gave correct answers on almost all the output that were generated for the question. And that's why we see the correctness reward function reaching 1.5 at the end of the training. You can find also the training loss is increasing. The training reward or the average training reward also increasing. That means that we trained or fine-tuned our model successfully. So moving now to the Kaggle training run. Let's also change here the settings of smoothing to running average. And as you can see here, we have a similar trend, an upward trend for each of the reward functions, as well as for the training loss and other reward functions. Alright, so now let's return to our notebook and test our model. So once the training run is completed, you can save the final LoRa using save pretrained, but you can also find it already saved in the output file with the different checkpoints. So for the testing, here we're gonna first test the model before training, and then we're gonna load the LoRa and test it after fine-tuning. So first we import the fast language model from Unsloth. Then we import the Qwen 2.5 model. We set it for inference. And then we ask it a simple question: how many R's are in strawberry? So once the output is generated, you can read it here. So we're asking how many R's are in strawberry, and the assistant answers with there are no letters R in the word strawberry. So then we need to restart the kernel and import our model using the saved LoRa. We're starting the kernel before doing that because the model is already on GPU, and if you try to run this cell without restarting the kernel, you would have an error where it would indicate that the model is already on the GPU or something like that. So here we import it from the GRPO saved LoRa. Then we set the model mode to inference, and we copy our system prompt to create our prompt where we ask it how many R's are in strawberry. And then we print the output. So here you can see the system prompt, the user question, and the assistant answer. So here we have the reasoning tag, only one, as we indicated. And then we have the answer. So the answer is correct. There are 3 R's. And then here we have the reasoning. So it says to determine how many times the letter R appears in the word strawberry. We can go through each letter of the word and count the occurrence of R. So the word strawberry has the following letters. And then counting the occurrences, we find that R appears 3 times. Alright, so that's correct. But one more thing I want to show you. We've trained the model to perform reasoning over 350 steps with 7 GB of VRAM over only 3 hours. So as you can see here, it trained for 3 hours and 3 minutes. And if I go up, you can see I've used only 1 GPU with max memory of 6 GB. Alright, so that's it for this video. I hope that you found it informative and you've learned a few new things, and see you in the next one.